Hi, my name is AGAM SINGH and this is Lab 5, Faraday's Law. In this lab, we try to explore the idea that Faraday's Law represents, and Faraday's Law relates time-varying magnetic field to a curly electric field whose path is integral around a closed path and is not zero, but it still provides an EMF that can drive a current. So we basically drop a magnet in a aluminum foil, and the interaction between the falling magnet and the tube produces an interesting result which we can explore in this lab. We collect observational data of the magnet falling. We model this magnet-tube interaction with a computational model, which will be shown at the end, and we compare our computational predictions with our data at the end. This slide shows fundamental physics concepts that were predominant in the lab. On the left, it shows the magnetic field of a current element, which you can see the formula. In the middle, it shows Faraday's law, which is negative n over the change in magnetic flux over delta t. And on the right, you see a variation of Newton's third law, which says every force or action has an opposite and equal reaction. For this lab, I found the length of the tube to be 0.27 meters, the width of the tube to be 0.8 meters, the radius of the tube to be 0.024 meters, mu to be 1.783 amp meters squared, which is what I got from lab 3, and the mass of the magnet to be 0.022 kilograms. These measurements will help with the computational model and to calculate anything for this lab. As stated below, this lab involves creating a aluminum foil tube and dropping a magnet down it and basically finding the total time it took for the magnet to fall into it. So the steps that we had to do to complete this was first mark the north pole of the bar magnet, and we did this by using one of the apps that we used in a previous lab. With one hand, hold the tube vertically and position the magnet just above the top opening, and basically you drop the magnet, and we recorded ourselves to find out this time code when the magnet enters the tube and the time code when the magnet exits the tube. And on the right you can see the 5 different trials I did and the average of those total times. On the left, you can see a diagram of the magnet falling through aluminum tube. You can see the magnetic force is pointing upward and the force of gravity is pointing downward, and you can see the net force is also pointing downwards. And I kind of took some observations during this time, and it took a while for the magnet to get down the tube, which was kind of interesting. And it turned to its side when it fell through, but then it turned vertical again. And they basically asked why we couldn't do this experiment with a ferocious tube, and I said that the magnet would stick to the sides of the tube and it wouldn't fall through, and we wouldn't get any time code of the magnet falling through the entire tube. This shows the code for my computational model that I created for this lab. You can see the measurements that we took before being used to create the aluminum foil for the lab. After that, we created the bar magnet. From there, we used our code from lab 3 to calculate the magnetic field of the bar magnet. Just a continuation of the code. On the left, you can see the calculation for d flux over dt. On the bottom, we had to create a loop to create this visualization. On the right, we had to calculate the gravitational force on this magnet, and basically at the end, we had to find the magnet's velocity and position, which created our graph at the end. And then at the end, it just prints time in the tube. And this was the computational output for this code. You can see the black cylinder, which represents the foil tube. The red rings represent the increasing current below the magnet. The blue rings represent the decreasing current above the magnet. And this just shows like how the magnet falls in the tube. So on the left, it just shows the model when it just started to begin in the graph that it created. And on the right, it just shows the model after the code had ran completely through and the magnet had completely fallen, and then the graph at the end, which just shows the velocity versus the time. In all, what if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? I said that the induced current would increase along with the magnetic force and the magnetic would fall slower down the tube. But what if the holes and slots were cut into the tube? How would this affect the ring currents in your model? I said that the resistance would increase, the induced current would decrease, and then the magnetic force would decrease, which would also cause the magnet to fall faster down the tube. Thanks for watching.